We're going to look at cell potential in this video. Now we've kind of mentioned that these galvanic cells are just redox reactions where the oxidation and reduction halves are separated and joined by some kind of a wire. And the poor little electrons are forced to flow from oxidation to reduction through the wire. So there's got to be some kind of a force then that's pulling these electrons through the wire. That's called cell potential. Its symbol is E cell. That little degree, don't worry about that too much. That just means everything is at standard conditions. And we'll talk about those in a minute, but it really doesn't mean like degrees Celsius or anything like that. So again, this is a measure of the pull on the electrons going through the wire from oxidation to reduction. Sometimes it's also referred to as the electromotive force, the EMF. If you're like a big physics buff, you may have heard that term before. But I think that's what's key. This is a force that's pulling the electrons through the system. It'll be measured in units of volts. All right. So in order to calculate the cell potential and kind of gauge, like, well, what is the pull drawing these electrons through the system, we look up something called standard reduction potentials. They're constants. For practice problems, you'll probably have to look them up on a chart. On the AP test, you will be given standard reduction potentials. And it's a measure of the tendency of a species to acquire electrons and be reduced. I mean, that's why they're called reduction potentials. It measures the tendency of a species to be reduced. And if reduction involves gaining electrons, that's kind of what we're looking at. Like, what is the tendency of this particle to be reduced or to gain electrons? There is a value for all species. Again, you just look them up on a chart. The more positive the reduction potential, the greater the tendency of this species to gain electrons and be reduced. When we say that the species has a greater affinity for electrons, it means like a greater attraction for electrons. And if it's a greater attraction for electrons, it's more likely that this substance is reduced. Okay, so here's how you calculate the cell potential. You'll look up these reduction potentials for each of your half reactions, and you add them. So E cell, the total cell potential for your reaction, is just the sum of the individual reduction potentials for each half reaction. Well, that sounds brutally easy, doesn't it? Well, it is. But there's one catch. And here's this reaction that we've been kind of looking at all along. This copper-zinc redox reaction. And we separated it into the two half reactions. Reduction involves gaining electrons. Okay, so we had mentioned that the copper half was the reduction half. The copper electrode increases in mass. The copper ions decrease as we run this thing forward. Okay, so that looks great. I mean, that is reduction. So this positive 0.34 volts, that's a number that you look up on a chart. There's a giant chart at the back of your study guide that looks like this. Wow. This is common half reactions. I mean, anything that you run into should be on this chart. Standard reduction potentials measured at 25 degrees Celsius. And so you would just look up this number. So you look up copper plus 2, gaining 2 electrons, forming solid copper. There she is. And then I get the reduction potential, 0.34 volts. Easy, right? Well, here's the only catch. In a redox reaction, there's an oxidation half as well. The zinc was the oxidation half, which involves losing electrons. So the zinc electrodes should decrease in mass as we form more zinc ions. Well, here's the problem then. These are called standard reduction potentials. So when you look this up on a chart, you're not going to find this exact same zinc half reaction. If I look this thing up, okay, where's zinc? Zinc, 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 zinc plus 2. Here it is. You're going to find this listed as a reduction half reaction, where the zinc ions are gaining 2 electrons. And then it lists the cell potential as negative 0.76 volts. Well, again, we mentioned that in a redox reaction, you will always have an oxidation and a reduction half. So all you got to do is look up that reduction potential and you flip it for oxidation. So when we looked this thing up, you're going to find it like this. In the reduction direction, plus 2 electrons, forming the solid zinc. And then this had a value of negative 0.76 volts. You will always need to flip one of these for oxidation. Okay, so if we know a reaction, and we know which one is the half reaction for the oxidation, we'll look it up and you just reverse the sign of the voltage. If we're really just reversing the reaction, instead of negative 0.76 volts for reduction, if I'm using this as the oxidation half, you just flip it. So we'll say flip for oxidation. You will always need to do this because whenever you look up those potentials, they're only in the direction of reduction. So you'll always have to flip the one that's oxidation. Then you really just add these. Well, that's not so bad. You add them up, and there's my overall cell potential. So I don't know if you noticed, like earlier on when we were looking at this picture, on the voltmeter it says 1.1 volts. So if I set this up and I let it run for a little while, hopefully it reads someplace close to that 1.1 volts. Okay, so here's some other notes on determining cell potential. It seems pretty simple, right? And for the most part it is. We kind of mentioned number 1. You will always need to reverse one of the half reactions for oxidation. So if you're reversing the reaction, you just reverse the sign of the voltage. Reverse the sign of the delta E. Well, that's not so bad. So this will always happen. When you look them up, they'll always be in the reduction direction. Okay, number 2. Since the electrons transferred must be equal. Do you remember how like sometimes you needed to multiply one of the half reactions? Now, that may not have applied in this one. It was a plus 2 plus 2. 2 electrons were transferred in each of the halves. But you remember how sometimes that wasn't the case and you had to multiply one of the half reactions to get the same number of electrons transferred? You do not need to do that here. This does not affect the value of the cell potential. You will never, ever, 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 ever multiply these guys. And that's a common mistake. That, people set up the 2 half reactions and then maybe they multiply one of them like times 2 to get 2 electrons transferred or something. And then they feel that they need to multiply the delta E value. And you do not. This cell potential is an intensive property, which means it does not depend on quantity or sample size, which here our sample size is really like the number of electrons flowing through the system. This cell potential is a force. The force pulling the electrons will be the same whether I'm pulling 1 electron or 2 electrons. Yeah, I'm like pulling more electrons, but the force pushing the electrons through the wire is the same. You will never ever multiply these cell potentials. A very common mistake though. You really just flip one for oxidation and add them. That's all there is to it. A couple things that are also interesting. Number 3, if a substance has a high reduction potential, which means that it would be like positive in a large value, that means it's very likely that this substance will gain electrons. It wants to be reduced. Well, if I look at that chart again, here's the largest. Fluorine's the winner. Well, does that make sense that fluorine really, really, really wants electrons? Yeah. Fluorine is a small atom with the highest electronegativity on the whole periodic table. Does fluorine want electrons? Big time, yes. The -1 fluorine ion is very, very stable. It's got a full outer shell, and it's very likely that it's going to gain that electron to fill its outer shell. So the more positive the cell potential, the more likely it is that that substance wants to be reduced. Now it's likely to gain electrons and be reduced. However, the opposite is true of something that wants to be oxidized. If you see a pretty low cell potential, or they even become negative, like here, the most negative, let's see if this is on the chart. Yep. The lowest cell potential is lithium, -3.05. Well, that means that lithium doesn't want to be reduced. Lithium does not want to gain electrons. In fact, lithium really wants to lose an electron. So now it's more likely that this substance loses electrons and will be oxidized. This would be a good multiple choice question where they may give you A, B, C, D. Here are these different cell potentials. Which is most likely to be oxidized? Which is most likely to be reduced? Well, they're called reduction potentials. So the higher the reduction potential, the more likely it is that substance will gain electrons and be reduced. And it makes sense that something like fluorine would have a high reduction potential. It makes sense that something like lithium would not. Why would lithium really want to be gaining a bunch of electrons? He's really more interested in losing electrons. Now, all of the alkali metals would like to lose electrons to fill their first energy level with just 1 electron. Lithium would really be interested in gaining 7 electrons. And it doesn't have a very positive nucleus, and it's only element number 3, so it's very unlikely that lithium would gain 7 electrons to fill the second energy level. Instead, he's going to say, let's just lose 1, and then I've filled my first level with 2. Lithium is more likely to be oxidized. These cell potentials will always run spontaneously in a direction that produces a positive cell potential. Your cell potential needs to be a positive value. When you add those together, if it's negative, that's not spontaneous. And we'll kind of look at that in a second. Well, how do I know if it's positive or negative? And here's that little degree symbol. Remember how we kind of said it has really nothing to do with temperature? That degree symbol, if you see E cell, I guess it kind of means that everything is run at standard conditions, and the temperature they're using as standard is 25 degrees Celsius, and all solutions are measured to be 1 molar. That's standard, and that's exactly what I'll use when we set up that zinc copper one. I'll use 1 molar solutions. Number 5, we'll look at that in the next video, that these things should run spontaneously in a direction that gives you an overall positive cell potential.